In this video, we will discuss Biot-Savart law. This law addresses the source or sources of magnetic field. In other words, what creates magnetic fields. Here we shall look at two sources. The first one is the moving charge. So a charge Q that is moving with velocity, say v, is a source of magnetic field. Namely, it can create magnetic field. The second is the continuation from the first, namely the electric current, I. Let's first look at how a moving charge produces magnetic field. Let's assume you have a positive charge like that, with a magnitude Q coulomb, and it moves along the dotted line with some velocity, let's say v. As the charge moves, it will create magnetic field B in a space around it. So since this magnetic field is a vector, we shall address the magnitude of it and also the direction of that magnetic field produced by this moving charge. Let's assume we ask the question, what is the magnitude of magnetic field created by this moving charge at this point P? This point P is at a distance, say, r, from where the charge is, like that. And the unit vector along that direction is, let's call it r hat. It is the unit vector in the direction from the charge to the point of observation, namely the point P. The magnetic field at point P is given by the following expression. A constant, let's call it mu naught, over 4 pi, the strength of that charge in coulomb, the cross product of that velocity vector and the unit vector r hat over the distance squared, r squared, where r is again the distance between the instantaneous position of that charge and the point of observation P. Now in this expression, the constant mu naught has a value of 4 pi times 10 to the power minus 7 in the unit of Tesla meter per ampere. Now this is known as the permeability of vacuum. Next, let's address the direction of this magnetic field. How do we define the direction of this magnetic field produced by this moving charge? It follows the right-hand rule. Grasp the velocity vector v with your right hand so that your right thumb points in the direction of v, like that. So the direction of your thumb is the direction of the velocity vector. Your fingers would then curl around this line of velocity in the same sense as the magnetic field lines, like that. So that is the direction of magnetic field. So if you have another point, let's say point Q over there, say at distance RQ, and the direction from the charge to point Q is defined by that unit vector, let's say r hat Q. The magnetic field at point Q would follow this same right-hand rule, and the direction is given by that arrow. So at point P, let's say, the direction of the magnetic field is tangential to that curve, like that, and at point Q, the direction of the magnetic field is tangential to that curved green arrow B in the following manner, like that. Next, let's look at how electric current produces magnetic field. Now, after all, electric current is a collection of moving positive charges. So if the electric current is going that way, that means you have a bunch of positive charges with certain velocity moving in the same direction. Using the same reasoning as before, if you have a point of observation, let's say P, over there, and we ask what is the magnetic field produced by this current element at that point P. The distance between that current element and point P is, let's say, r, and that direction is defined by a unit vector r hat. The magnetic field at that point P, let's call it B, is defined by similar equation as presented for the charge, namely mu naught over 4 pi times the electric current, the length vector, the direction of this length vector, with the length dl, is in the same direction as the current, cross into r hat over the distance squared. This equation is what we call the Biot-Savart law. It enables you to calculate the magnetic field produced by some current element with the length dl at point P, a distance r away from the current element. So in a case where you have a very long wire extending to infinity in both directions, carrying current I, then the direction of magnetic field that this current produces at, let's say, point P will be in a direction that is tangential to such curves. So this is the magnetic field lines, and at point P specifically, the direction of the magnetic field would go like that. And it's important to realize at various distances, these curves are just part of circular loops, and that defines the direction of the magnetic field lines like that. And the strength of these magnetic field lines is of course dependent on the distance from the current element. The further away the point of observation, the weaker the magnetic field gets. Let's look at the following exercise. 2 protons, 1 and 2, move as shown in the figure below. So the upper proton is moving to the left with velocity v, and the lower proton is moving with the same velocity but in an opposite direction. At the instant shown, namely at the instant where these protons are vertically aligned like this, find the magnetic force on the upper proton due to the magnetic field of the lower proton. So of course step number 1 is to figure out the magnetic field produced by this proton at that location. And we can easily calculate that. Let's call that magnetic field dl, and we know it is quite simply mu naught over 4 pi, the strength of the lower charge, q, the velocity of the lower proton in terms of I hat j hat notation. So since this is the x-axis, the unit vector is I hat. That is the y-axis, the unit vector along that direction is j hat. The velocity of this proton can be written as vi hat cross into the unit vector along the direction from the lower proton all the way to the upper proton, and that is quite simply j hat, the unit vector along the positive y-axis, over the separation distance between this proton and the point of observation, namely the location of the upper proton, is r, and square that. From vectors we know I cross j is quite simply k hat. So this magnetic field can be written in the following manner: mu naught over 4 pi q v over r squared k hat. So the magnetic force experienced by this proton, let's call it Fu, is quite simply the strength of that proton, the velocity of that proton, so velocity is given by that, so in I hat j hat notation is v times minus I hat because the upper proton is moving in a leftward direction, cross the magnetic field at the location of the upper proton, which is BL that we have just computed. Substituting the expression for BL into here, we get mu naught over 4 pi QV over R squared minus I hat cross into K hat, which is just J hat, thus giving us the answer for the magnetic force on the upper proton due to the magnetic field of the lower proton. Problem 2. A wire carries a steady current of 100 ampere as shown like that. Find the magnetic fields produced by a 1 cm segment of this wire at 2 points, point P1 and point P2. P2 is right there, and both these points P1 and P2 are 2 meters away from the current element. Of course, the equation to use is the Biot-Savart law, which is mu naught over 4 pi, this is a vector equation. The current element cross into the unit vector of the point of observation from the current element over the distance squared. That means the magnitude of the magnetic field is quite simply given by the following expression in the numerator, is dl sine alpha, where alpha is the angle between the current element and the unit vector defining the point of observation. So let's do point P1. The magnetic field at point P1 has the following magnitude. So mu naught is a constant that we already know what it is. The current is 100 ampere. The length element has the length of 1 cm, so convert that into meter, 0.01 meter. Sine, now what about the angle? Note the angle between this current element, which is going like that, and the point of observation is vertically upward, so the unit vector along that direction is like that. The angle is 90 degrees, so sine 90 over this distance, which we know to be 2, and square that, which will give you 2.5 times 10 to the power minus 8 Tesla. The direction of magnetic field at point P1 from the right-hand rule would tell you is going into the plane of the computer screen. We can also see that this is the case by doing the cross product between dl and r hat in this case, which is 90 degrees with respect to each other. So when you curl from dl to r, you can see your right hand thumb is pointing into the board. Now let's look at point P2. So the magnitude of the magnetic field at point P2 is again given by mu naught over 4 pi times the current element, which carries a current of 100 ampere. The length of that current element is 0.01 meter, so 1 cm converted into meter, times a sine of the angle, in this case the angle between the length vector and the point of observation direction is 20 degrees, so sine 20 degrees, over the distance is again 2 meters, so 2 squared, which will give you 8.6 times 10 to the power minus 9 Tesla. The direction of magnetic field at this point is again given by that cross product between dl and r hat. So when you curl using your right hand, your fingers from dl to vector r hat, your thumb will be pointing again into the board. So the direction of the magnetic field at that point is also going into the plane. Thank you for watching.